Hello everyone and welcome to Exploring Diana YouTube series where we explore the powerful capability of Diana one step at a time. My name is Solmaz and today I will go over one of the tutorials in Diana website. The title is Bonded Slip of a Post-tension reinforcement in two-dimensional elements. Let me describe the problem and after that I will jump to Diana environment to start the simulation. In this video, I want to analyze a 60-meter concrete beam with a post-tension tendon. It has a two 30-meter span and a non-symmetric I-shaped cross-section. You can see the geometry of the post-tension beam on the screen. As you can see on the screen, in this geometry, the tendon follows a curved path and is tensioned from the both ends at the same time. During the post-tensioning, a few key effects occur. The first one is related to the friction between the tendon and duct, which reduces the tension force along the length. The second key point is related to the jacket, which apply an equal and opposite force on the anchor, which shorten the beam and cause more force loss. And the last key point is related to the when the final stress is reached, the tendon is locked and grooted. Let's take a look at the key feature of the post-tension beam model in Diana. The tendon is modeled as a truss bonded slip reinforcement. Using the truss bonded slip reinforcement Diana means that the slipping between the tendon and concrete is captured by using the special interface elements. The normal traction regarding to the displacement is modeled as a linear elastic, while the shear traction regarding to the slip follows a nonlinear cubic law, which is introduced by Dwyer, and you can see the graph related to the cubic function by Dwyer on the screen. For more explanation regarding the model that we have in Diana, for modeling the bonded slip reinforcement, you can refer to one of the tutorial in Diana. The title is Bonded Slip Models in Diana. In this model, beam is built with the 2D plane stress element and support are placed at the both end and the mid span with a vertical and horizontal constraint. And we use the elastic steel plates for realistic support behavior. I want to simulate the model in two phases. In the first phase, the tendon is jacked from the both ends with a nodal force, and a weak bond is defined between the tendon and concrete since it's not grooted yet. In the phase 2, the tendon is grooted and the bond properties are made stiff, and jacking load are removed and tendon is locked at the anchor location. And a vertical load is applied at the middle of the left span. As you can see on the screen, we have a material properties table for this model. We use the FIB model code 2010 grade, the concrete grade C55 for the beam. And also we have two different material properties for the bonded slip reinforcement. The first in the first phase, we have a weak bond, which the tendon is not grooted, and in the second phase, we have a stiff bond that the tendon is grooted. When the tendon is grooted, okay. Now I want to move to Diana environment to start the simulation. So this is a Diana environment. In Diana, to create the geometry, we have three options. The first one is using the action toolbar in the right side of the window. The second one is using the Python scripting and command console, and the third one is importing the CAD file. For this video purpose, I want to save time and use the Python scripting to create the geometry. So I just need to copy and paste the Python script to the command console and wait for a second until Diana create the project and geometry. Yes. Now we have a geometry in this model. Let me explain what we have up to now, and after that I move to the next step. I come to the edit project setting. In project setting, in analysis model, we have a structural analysis. It's a two-dimensional problem. And for the measure type, I use the hexahedron quadrilateral measure type. And for the meshing order, I use the linear meshing order to simplify the simulation. Also, we have a different part of geometry on the screen. We have a bottom flange, web, and top flange of the concrete beam. We have a curved tendon. We have a support plate in the left, right, and also middle of the span. And also we have an anchor plate in the left and right of the tendon. So we need to assign the properties to the geometric shape. The first object that I want to assign the material properties to them is related to the concrete. Since we have a different thickness for the bottom flange, web, and top flange, we need to assign the separate material to each of them. So the first one is a bottom flange. I come to the bottom flange. The element class is a regular plane stress. And for the material, I need to define the material properties for that. I call it concrete. In the class of the concrete design code, I select the FIB model code for the concrete structure 2010. And we don't have any aspects to be included in this model. And yes, we have for the concrete class, I select the C55. And for the cement type, I select the normal hardening cement type. Very good. For the geometry, I call it thickness bottom flange. And the thickness of the bottom flange based on the geometry that you have seen in the first slide is 0.8 meter. Very good. I come to apply. The next object that I want to assign the properties is the web of the beam. I select the web element class regular plane stress. For the materials, I select the concrete that I have defined in the previous step, and for the thickness, I call it thickness web. And the thickness of the based on the geometry is 0.2 meter. And the last object related to the concrete beam is a top flange. It's a regular plane stress and the material is concrete. And for the thickness, I create the name thickness top flange. And the thickness of the top flange is at 0.5 meter. Very good, we have assigned the properties to all three parts of the concrete beam. Now I come to the material properties for the tendon. To define the material properties for tendon, I need to come to the reinforcement properties. For the type, I select the truss bondancy, and we need to define the material and geometry for the tendon. So for the material, I call it weak bond. As I mentioned in the earlier slide, we have a two phase in this simulation. In the first phase, when the tendon is not growthed, we define the bond slip truss bond slip reinforcement with the elastic properties for the tendon and a weak bond interface properties for the interface and bond slip interface. So for this purpose, okay, we need to define the Young modulus 2.1 E11 mass density 7,850, and for the nonlinearity of model I select no nonlinearity. But for the bond slip interface, I need to define the stiffness modulus in the normal direction. For the normal direction, I input the parameter as a 1E12 And for the shear stiffness modulus, as the input data 2E6. And for the bonded slip interface failure model, I select the cubic bonded slip function by Doer, as I mentioned in the first slide. And for this purpose, I need to select the parameter C. I input the 20, and also shear slip at the start plateau is a 10 meter. And also, I want to enable the option reset the state parameter on material change. This is important because it allows us to simulate the growing process without creating artificial stresses. So when we switch from the weak bond interface to the stiff interface after we apply the growing to tendon, it won't generate extra stress or strain in this model. So the next is related to the geometry. Okay, for the geometry, I call it truss bond slip. And for the type of reinforcement, select the truss bond slip. And for the input data regarding the tendon, I select the diameter. And the diameter of the tendon is a 0.06 meter. Very good. Now we have material properties and geometry for the tendon. As I mentioned in the modeling approach, we have a two-phase in this simulation. In phase 2, after the tendon is growted, we need to define a new material properties with a stiff bond slip interface. So to do this, we can simply come to the material and duplicate the weak bond material, rename it to the stiff bond. And also we need to change the bond slip interface data. For this purpose, I need to increase the shear stiffness modulus to 2E10. And also we need to set the slip at the start plateau to the more realistic value of the 0.1 meter. Very good. Now we have a stiff bond material and weak bond material properties for the tendon. Now I come to the geometry and I want to assign the material properties to the remaining part of the geometry. So I select the shape properties and select the support plate for the left, right, and the middle of the span. And for the material, the element class is a regular plane stress, and we need to define a new material. I call it steel. In the class of steel, and for the material model, I select a linear elastic isotropic and input the Young modulus, Poisson ratio, and also mass density for the support plate. For the geometry, we need to define the thickness of support plate, same as the bottom flange, 0.8 meter. I come to apply. For support definition in Diana, I come to the support. As the first step, we want to restrict the translation in a y direction at the middle point of the tree support plate. After that, we need to restrict the translation in the x direction of the middle support plate. So for this purpose, for the first restriction, I call it vertical support. Then we need to set the support at the support set. I call it supports. The target is a vertex, and I select the middle point of the supporting plate and fix the T2. The second one is a horizontal support under the previous support set, and for the vertex I select the middle point of the middle support plate and fix the T1. Very good. Now we have a boundary condition in this model. In this step, I want to define the load to this model. So the first load that I want to assign to the model is a self-weight. So I come to the global load, I call it gravity. And we need to set the load case for that. I call it gravity. And after that, I come to create. The next load that I want to define this model is a pre-stress load. So I call it stress. We need to define the load case for that. The target is a shape and the load type is a reinforcement bar pre-stress. And for this purpose, I select the tendon and assign the pre-stress in bar to the model. So 1.5562E9. Very good. The third load that I want to define this model is a pointed load. But before that, we need to set the location for this concentrated load. A concentrated force is applied at the in the left middle of the left span. So to do that, I come to the point. I call it point 1. The input is single and the location is 1.4. Create. Now we have this point in the left span, and also we need to project this point on the top flange of the beam. So the target is a top flange of the beam and the tool is a point 1, and the direction is 0 minus 1. Very good. So again, I come to the load. I call it point load. Also, we need to define the load set for that. The target is a vertex. Load type is a force, and for the vertex, I select the vertex of a top flange, a point that we imprinted on the top flange. The value is a minus 2.5 E6, and the direction is a Y. Very good. Now we have a pointed load in the left span of the beam. After a load assignment in this model, we need to create the load combination. So I come to the load. We have a 3 load cases: gravity, pointed load, and also pre-stress load. For the load combination, the first load combination is related to gravity. The second one is a gravity plus pre-stress, and the third load combination is related to the pointed load. In this step, before generating the mesh and set up the analysis section, I want to do some adjustment in this model. The first modification that I need to do is related to the anchor plate in the left and right side of the beam. This plate is generated because of the old implementation in Diana. But due to I use the new pre-stress load definition in this model and I'm using the new implementation in Diana, so I don't need to these anchor plates anymore. So I delete these two on geometry level. Very good. After that, I need to do some adjustment in material properties. First, I'm going to the stiff bond and I need to select the anchor aspect. In the anchor aspect, I have to define the spring stiffness in the N and S direction. So 1E12, sorry, 1E12 for the N and the 1E12 also for the S. And at the beginning and end of the bar and with the no failure model. I need to do this adjustment also in the weak bond. So I consider the anchor in the aspect to be included in the model. And again, I input the N and the S for the tendon and need to be added at the beginning and end of the bar with a no failure model for the anchor. Very good. Everything is ready to generating the mesh and set up the analysis section. In the next step, I want to generate mesh to this model. So I come to the mesh properties and also I select all objects in this geometry. In the element size, I select 0.15 meter and come to upload. Now I want to generate mesh. Wait for a second until Diana generating mesh for this model. Now we have a mesh generated view of the beam and other geometry object. Now I come to the analysis section and describe what we have in this section. We have a phase analysis for simulate. In the first phase, I don't have any anchor plates in the left hand light, so in the first phase I have all material included, but the difference with the first phase and the second phase is related to the material for the tendon. In the first phase, we consider the weak bond, and after growing and fixing the tendon, we use the stiff bond for the second phase. So if I want to show you what we have in this result, for example, I come to the displacement in the y direction. And in the last step of the phase, like step 2, we have a 0.09 meter displacement in the y direction for tendon and also for the beam. And if I want to show you the other result related to the reinforcement cross-section forces, NX, and just let me show in a line diagram to have a more clear view. And if I come to the end of the first phase post-tensioning, we have a 4.21 E6 Newton for the cross-section forces. Now I come to the end of the simulation. We have a result. So just one more thing that I want to mention is related to finding the tutorials on Diana website. So in Diana website, you can go to get started in the tutorial section based on the tutorial type, tutorial analysis type, for example, nonlinear analysis, modal response, and modules required. You can find your desired tutorial. Very good. Thank you for your attention. Please subscribe Diana YouTube channel. Thank you. Bye.